We start. I have the announcement regarding to the midterm exam. We are going to have a midterm exam as scheduled on the Tuesday next week in this classroom during the class hour, which means we are going to start on time 3 o'clock and end the exam 4:15. The exam will cover the chapter 1 through 6, not 7. So 7 will be part of the final exam. Okay, so don't worry about the next chapter that we are going to discuss today. So chapter 1 through chapter 6. The exam consists of the two parts. One is the multiple choice. Multiple choice is 15 to 20 questions, and you can select one of the best answer from the multiple choices. Then it's usually the 40%. So then the other 60% of the exam will be based on the open-ended question. So probably I can make the 4 to 5, depending on the time. By considering the time, exam hours, so it can be 3 or 4, around the 4 questions, 4 or 5, or the 3 or 4, around the 4. I don't make the question yet, but each question will be worthwhile the 10 to 15 points. So you can imagine what kind of the open-ended question. If you successfully did the lecture and the homework quiz, so you can easily answer such a question. Any question?
Multiple choice. Multiple choice questions.
Yeah, multiple choice. So, open-ended questions. So for example, this will be the good example that I'm going to make this process the state. Then what is the average waiting time? Something like that. Okay. Yes.
Are we going to different exam for graduate and undergraduate?
Oh yes, that's another thing. So this is the close listed between the 308 and 503. So I will definitely consider the separately undergraduate and graduate student in case I need to apply the curve. So I usually apply the curve if the performance is not so good enough. I target on the average. The overall average is the upper 70, just below the 80. If that is not reached, I apply the curve separately, undergraduate and graduate student. Any other, but in terms of question, it's the same.
Same exam.
Yes. Any other question? Okay, then on Thursday, so if we finish the lecture this week regarding to the chapter 7, on Thursday, we are going to check the midterm exam. So do not miss. That's the only time to check your midterm exam sheet. I'm not going to assign the separate time. So do not miss the class on next week, Thursday, to check the midterm exam sheet. Okay. Any other question? Okay. Then the last thing, if somebody asks the question, how do I prepare the midterm exam? Best way is as I said, textbook. Okay, so it's totally up to you whether you study or not, or even you study only with the PPT file. But the PPT file is a supplementary, okay, to help my lecture. Okay, it's not the primary material for your study. A lot of missing in the PPT file, and sometimes the error. Okay, while I prepare the contents of the PPT file. Okay, so do not take the complaint based on the PPT file. So PPT file is always the supporting material. Okay. Any other question? Okay, so we'd like to continue the remainder part of the CPU scheduler. So we are discussing about the real-time scheduling. And the most important part of the real-time scheduling is whether we can make the deadline or not. Okay, that is the key part. It doesn't matter. The faster the better, but the faster, how much faster is not the critical in the real-time operating system, real-time scheduling. Two others, the problem of the such a real-time schedule. Also, when we are saying the real-time operating system, mostly the main difference between the general operating system, real-time operating system means is the scheduling. Whether scheduling the guaranteed deadline or not. Okay, so we can consider first the priority-based scheduling. In the priority-based scheduling, first we are going to consider the certain amount of the CPU, the time that is the period. So periodically, at least each processor should get the CPU like this one. That we have the one certain period time, period 1, period 2, period 3, and at this time the processor need to get this amount of the time, okay, CPU time, which is called the rate of that. Okay, to implement when we implement this one, okay, the first approach is whether we consider the shorter period time, shorter amount of time of the process as a higher priority. Okay, shorter period will get the higher priority. For example, in case we have the two processes, the period of the P1 and the P2 is here. The P2's period is the longer than the P1, which means P1 is in a hurry to finish the due date. So we can select the P1 is the first, then P2. At this time, okay, P1 is shorter, so P1 is selected, and P2 something like that. Okay, that is one of the way. But sometimes you cannot guarantee all the process make the due. Okay, in case this kind of real-time scheduling is called the soft real-time. We try, but we cannot guarantee all the processes. Question?
Yeah, at time 50, you check another time which process is shorter, right? Or not?
Yes. Okay.
And in that case, it's P2, right? That's
the
priority.
Anyway, so this time the shorter, because P1 and P2 already got the CPU resource. At this time, when you check that, which one is a shorter period?
And it's P2.
Yeah. P2 is the longer. The periodic means it's a fixed amount of time. Okay, so within that time, periodic time, each processor should get the certain amount of CPU time. That is the T in this case. Okay, so P2 has the longer periodic, then it has the lower priority. Okay, but it may have the problem like for example, if the period of the P2 is the middle. The P1 is selected, right? Because P1 has always the higher priority, shorter the period. So P2 may not get the full CPU time, which is not the completed. So also to address that problem, so we can consider always the deadline. Deadline is which one will be finished. For example, at this time, P1 will be deadline, the periodic here. Okay, P2 is here, so P1 will be selected because the P1 will be has the earlier deadline than the P2. And this time, the P2 will be selected, P2 deadline here, and new deadline of P1 is here, and so on. So this is another approach to guarantee the real-time operating system. Is that all for the real-time operating system? Definitely not. This is just a small example of that. So if you if you are interested, it's I think the one separate textbook for the real-time operating system. Okay. So I'm going to skip the example of the operating system regarding to the scheduling, but because we already discussed most of them, so you can quickly go over and read the example of the Solaris and Windows. Then jump to the evaluation. Once we have the algorithm, this is the same the process as the research. If you are doing the research for your master thesis or as a PhD student, so what is the research? Research is if we can find the problem, okay, in our daily life or real life or nature or computer, whatever. If we can find the problem, so we are going to make the hypothesis. So if we apply the Gaussian, the mixture model to classify the student, we can have the good clustering, good grouping of the students, something like that. Then we apply such an algorithm, the Gaussian mixture model for the clustering or grouping the student group. Then we have the result. How much good? How good the cluster is, how good my algorithm is, how good my research is. We need to evaluate. We need to check whether this is a good approach, whether the result is the hypothesis is true or not. We need to evaluate. So this is a general evaluation method It's not only for the CPU scheduling, it can be used for any other research also. So by focusing on the CPU scheduling, for example, I have the new CPU scheduling algorithm. Not right now. I believe that I can say that there are many the researchers who developed the new scheduling algorithm. It's not general, but focusing on the specific task, like the real-time operating system or embedded system or the mission critical system, whatever. But still, there are new every day. The CPU scheduling algorithm, they claim their algorithm is better than other. How can evaluate? How can promise their algorithm is better? There are 4 different approaches: deterministic modeling, queuing model, measurement from the implementation, and real implementation. The first one is the deterministic modeling. It's the same approach as what we have done before. How do we evaluate the CPU scheduling algorithm so far? We have list of process 0, alive time 0 with the CPU burst time, the 10, and the priority 1. Process 2, alive, and so on. So we have the list of process. Then check each algorithm. Then calculate the average waiting time of first come first serve and the average waiting time for the shortest job first. Then my new algorithm. If my new algorithm provides the less waiting time, mine is better. Just like that. By applying the same deterministic model, deterministic means it's a fixture. Okay? So there's a ground truth, there's the fixture is not variable, so we can evaluate the algorithm. That is a deterministic modeling. Okay? It's kind of the analytic evaluation. So that can be applied to any research. So we have the sample data set and apply and compare with the existing one and new one, which one is better. So this is a deterministic model. So we did the same approach in the chapter 6. And queuing model. Anyone who ever used the queuing model? Or anyone who heard about the queuing model? No one? What is a queue? Queue. First come, first serve. Right? It's a data structure. And queuing model means it's a model. What kind of a model? Mathematical model, specifically statistics model. Okay? It's a statistical model for what? Coming. We'd like to model how often the data or customer in the, for example, the McDonald's. In the McDonald's store, do they consider the randomly how many registers are needed and how many the part-time register are hired, just random or experience? No. They actually model. Model based on what? How many incoming customers? Okay? How many? Certain period of time. And how many of them are wait? Okay? Queue. First come, first serve. And how many of them are processed? Okay? The longer queue is the better? Definitely not. So the shorter or nothing in the queue is the best one. Nothing is the best one? No, it's a waste of register. So we can define, there might be another code. I know who he is. It's actually my old university. They call every other week the same time. Then ask what? Donation. Okay. Anyway, so we model incoming data and length of the queue and how much it process using what? Mathematical model, statistical model. At that time, certain distribution will be used. That is the queuing model. Okay? We don't have to evaluate using the deterministic, the whatever, just using mathematical model. If we are using the statistical distribution, for example, Gaussian distribution, if follow the Gaussian distribution, how many parameters do we need to define the Gaussian distribution? Mean, average, and variable at the variance. Mean determine where. This is a Gaussian distribution. This is the mean value, and this is the variance. 2 parameters. Only using the 2 parameters, we can represent such a income and outcome model. This is just an example. We can use other distribution. Usually, this exponential model is used for such an incoming customer, and also it can be used for what? Network model. Network has a lot of incoming data, packet, number of packet, and outcome, sending the data. And that determines what? Bandwidth. Okay, you can design, model the bandwidth using queuing theory. Nowadays, the queuing theory is very, very important. Many applications. It's actually one subject in computer science. So we can use such a queuing model. Why? The incoming data considered as the process. And process is the algorithm, and waiting time, we can consider how long wait. So queue size. Something like that. Anyway, that's the mathematical model. Sometimes it's different from the real situation. So nowadays, we can use simulation also. Simulation means it's not real implementation. We program like your project 1. In your project 1, you simulate the CPU scheduling algorithm. Right? It's not real, the operating system, but you simulate only the CPU scheduling algorithm. That is the project 1 simulation. Benefit, we don't have to implement the real operating system, right? Instead of focusing on that algorithm. So maybe easier than the real implementation. Problem, still this is not the real. Sometimes it's different from the real situation. Okay, depending on the parameter value and condition. But it's a user network simulation. If you go to the technology building, you can see bunch of poster. Do you think all the poster implement the real algorithm? No, many of them use the simulation to evaluate their approach. Finally, if the algorithm, I'd like to implement the scheduling algorithm to detect the nuclear plant. It's very, very critical. If something 1.001 error, it will be disaster. So at that time, you need to implement a real system and test it. That is the real implementation. So you can use one of these. This idea can be used for any research area. Okay, so you can use a real implementation, sometimes a simulation, sometimes the mathematical modeling, and sometimes you can apply something queuing model and something like that. Quite deterministic. This is one good example for your understanding the CPU scheduling algorithm. Also for your the understanding of the project 1. I'm not sure whether I can connect the internet. Is it connected? So wireless? Is it connected? Oh yes. So if you go to that website, the link, it has the CPU scheduler application. So unfortunately, I think when I test my browser, cannot run the applet. So I'm going to make sure whether I have. Where is it? Okay, this is a simulation of the CPU scheduler. So, for example, I do not have the data, the deterministic data, so randomly generate data source, and option show that this is a creative data, so which means first process alive, okay, CPU burst time 6, second, this is once, it's a priority in this case. This is a priority, and the size of the bar is the CPU burst time. Then you can select the algorithm that you implement, like the first come first serve. Should is the first round robin and priority. Which one do you want? For example, first come first serve. Then you can. So you see this one is used, and next. And you can see the CPU time and response time, turnaround time, wait time is calculated. This is what you are going to do in your project. Okay? Main part is not the graphical user interface, so whether you can implement algorithm. Okay? I believe that you understand the algorithm itself, but the problem is whether you can implement such an algorithm with your programming language.
So this one are just the sample data, right?
Yeah, this is just a sample, randomly generated data. Okay. So this is a first. Once this is done, you will see the statistical data. Okay. So this is one of a good reference for your project one. These are the list of the process in the queue, ready queue. Okay, the blue one. So this one is not alive yet. Okay.
No, but I mean, the bar is reducing, that means it's executed. Right?
Yes, because I set the time frame speed. Okay. So it's not critical in your process. Can be quickly done if without such a time frame. Okay, then once this one is finished, then you can see the total CPU time, idle time, and response time. The average is the 193. I don't know what is the unit, but anyway, so you can see. So let's do the same data set but different algorithm, round robin. So let me change one. You don't have to, sorry. This is the current source. Then is it running? Doesn't work, run it again. That is the best way. Oh yes, it's running. Okay. Oh, it's so slow. It's slow. I think that you can see it. It shows the. Did I check the round robin? Yes, round robin. So these are the process in the queue. So you will see it's take time. It's a round robin question. Okay, for the process, and you can, even though we use the different data set but randomly created, so pretty much it has the smallest mean time, mean of the response time.
Is it the shortest job first is the most optimal route?
Oh yes, sure is the remaining time. Okay. Okay, so that's the end of the chapter 6, and your midterm exam will cover up to this part. And next chapter is for the deadlock. Okay. So we already during when we discussed about the semaphore, so synchronization problem. So we talked about a little bit about the deadlock situation. So in this chapter, we will formally define what is the deadlock and how to address the problem of the deadlock in our operating system, because that is the critical. If we do not address such a deadlock problem, is the entire system maybe the stop, the hang. So okay, so what is a deadlock? So as we most of the time, most of the chapter, I'm going to mention about the one thing. Operating system is a very limited resource, but we have the many consumer processes that cause the problem. It's the same thing in the deadlock problem. So since we have the multiple processes, but they try to share the shared resources. So we have the, for example, in case of the semaphore, so we have talked about the process 0 hold the A, so A, and process 1 hold the B using the wait method operation. Then the request the semaphore B, and which is held by P1, and the P1 is request a wait for the A, which is held by the process 0, which means both of the process are waiting each other forever. Because if no process the release there, the holding the semaphore, it will be forever. This is called the deadlock situation. Okay, we need to solve that problem. Otherwise, your system will be stopped. So we can understand such a deadlock in our real life also. So if we have such a bridge, you can see such a narrow bridge in the suburb area, or if you go to the Milford is under construction, one of the middle next to the 95, wherever. But anyway, which means we can consider each car as the process and the lane as the resource. Okay, so this car is holding this resource, and this car is holding this resource. They are requesting the other side. Okay, so if one of the car, unless one of the car back up, there's no way to proceed to the other. This is kind of the two process cases. What about this one? This one is the kind of Manhattan. Okay, if you drive to the Manhattan, this is one block building, and you encounter such a problem. This is called the gridlock. Gridlock is used for such a case. It's just one example. If you read something in the newspaper article, the gridlock means it's a chain lock. Okay, so consequently happen, and finally, it's the worst case. What can be the solution? Policeman. We need a policeman. So this is multiple process case. So this is usually happen. So we will see. But in this case, even we can consider the lane of the car as the one process and this road as the resource. Sometimes we have the multiple resources, but they may cause the deadlock also. So we will see such a cases. How? So we try to model, just like the other the computer science problem. The first thing is whether we can define the problem using the model. So we can consider resource as R. So we have n number of resources, R1 through the Rn, such as the CPU can be resource, and I/O can be considered as a resource. Memory it can be considered as a resource. Hardware only, no operating system or software, like the data structure can be considered as a such a resource. Anything that can be considered as a resource. Okay. Sometimes we have several different I/O devices. So each resource may have a number of instances. Okay, for example, hard disk drive, hard disk drive 0, 1, 2, 3, something like that. At the time, we can call it the instances, W instances. Okay, then each process to get the resource of the computer system, so we need to request. Okay, we need to request, then use and release once it is done. This the basic process is the same as no matter what. Sometimes we can use the different command like to open the file and use it and close the file, or allocate the memory, analog function, allocate the memory and use the memory and free the memory. But all of these are same concept: request, use, and release. Okay. So that is the definition of the operating system to define the deadlock. Then how can we define the deadlock? If the process and the resource satisfy these four conditions, we can say this is a deadlock situation. It's a deadlock event. First, the mutual exclusion, which means only one process can take the one resource, instance especially. Okay, if the resources are shareable, there might be shareable resource like the memory location. If you allow other process access the data, it's a shareable. But in that case, if the resource can be shared with others, there might be no problem. There's no deadlock. No matter how many processes request that resource, you can allow. There might be no problem. So mutual exclusion means only one process can take the resource. If you have the multiple instances, that means one instance of the resource. Okay, that is a mutual exclusion. Second requirement is process need to hold one request the other, hold and wait. Okay, then that requested resource should be occupied by the other resource. So which means you need to wait. Otherwise, if we do not hold anything, you may not close the deadlock because you are not involved in such a deadlock situation. You need to hold something, resource. Then request that should be, you should wait for that requested resource. That is a hold and wait.
So
okay? Yes.
Process 1 is holding a resource.
Yes.
Then process 2 is probably waiting for that resource to use.
Yes, we will see. But that is the two process cases. But we may have a number of processes. So we try to define the deadlock situation in general. The two process case is easy to understand. So one process, as we have seen before, like this one, it's a very simple case. But in general, like a number of the processes, a number of resources, a number of instances. So in that case, how can we define? So in case the process satisfying with the mutual exclusion, and next one is a hold and wait. The third one, let's take a look at the third one. No preemption means it's no backup, okay? No preoccupied, which means, so if you allow the preemption means, so you can release the resource that you are holding, okay? Then later you can take it. That is a preemption. However, if you allow such a preemptive process, which means if you release the current resource, the other process can take that resource. There might be no problem. So it may not cause the deadlock. So to make the deadlock situation should be no preemption, which means do not the release current one. Okay? You cannot guarantee whether you can preempt that resource later. No preemptive, no preemption. Okay? It's a greedy. Okay? So if I keep the current resource, I never release. Just like in this case, in case of this one, this lane will not back up. Cannot be back up, right? So if you can back up, so this lane go through, and this lane, there might be no problem. But in case of deadlock, they never be back up. Back up, so that may cause the deadlock. That's enough? No. One more thing is, they are waiting. So we have the hold and wait. So I'm holding the resource and wait. He's holding the resource that I'm requesting, but he's requesting to the other, and the other, that's it. Then what happened? She can take the resource, he can take the resource, then finally I can take the resource. So there might be no problem. To be a problem to make the deadlock, he need to ask mine, which means should be circular fashion, circular way. So four conditions to be in general to be a deadlock event. First one is mutual exclusion, non-shareable the resource, especially non-shareable the instances. Second is hold and wait, and there should be circular way, and no backup, no preemptive, no preemption. Do not release in the middle. So that is the four requirement of the deadlock. Let's go back to this example. So first one, mutual exclusion means I do not share this load with other. That's the mutual exclusion. Second, hold this lane and wait the other lane. Hold this lane and wait the other. And they are circular fashion, right? And also no backup. Then this is a deadlock. Yes?
No, but it's no backup, but once you acquire the resource and once the process is complete.
If you can get the resource, which means if this lane of the car take the lane, then it will be done. But no way to take this one because they are waiting each other like the snake. Okay, so what about this case? So same thing. It's a deadlock. What? First, mutual exclusion. One resource. This is a lane. This is a lane. Each car take and hold and wait. Hold and wait. And it's a circular. Even though two process case, it's each other. It's a circle. Hold and wait. And they don't wanna back up to the other. Do not release. So this is a deadlock situation. This is a general definition of the problem of deadlock. So that's not the main thing. Main thing is how to address that, solve that problem. The easiest way is what? Avoidance. What does it mean?
Should avoid the deadlock and move further. Like no deadlock occurs.
Yeah, that's my question. How to avoid that deadlock?
We can assign some resources for the particular processes, what we can do, or else we can wait for one process to finish and then we can give resources to another process.
I think the similar, okay? Which means that her opinion is making sense if we consider based on this definition. So if the current status of the process satisfies with all these conditions, that is a deadlock. In other words, if one of these requirements is not satisfied, What does that mean?
It's not a
It's not deadlock. So we can break disobey one of these. That is deadlock avoidance. We can avoid the deadlock. How? By allowing at least one of these. For example, mutual exclusion means it's the one process take the one resource, not share. Why don't you make shareable device? Why don't you make the shareable structure? Why don't you make the shareable resource? Then no deadlock. Sometimes possible, sometimes not. Right? CPU time, CPU cycle cannot be shareable, right? So some of the resources are possible, sometimes not. So you can allow one of these. So what about the hold and wait? You can have the operating system policy like that. You cannot hold the resource until all resources are available. So in other words, to get the resource, like I need to process the series of instruction threads, okay, I need to access the shared data, semaphore, and access the hard disk drive 0 and CPU time, the 10, and that's it, memory, okay? Then check whether semaphore is available. If yes, check that this the hard disk drive, CPU time, and memory. If in case all of them are available, then process.
what?
Available resource.
Who is using what resource?
Nobody use that resource, only me. I'm the process. Okay? I never hold the data, right? Until all resources are available. That makes sense. But that avoid the deadlock problem. Sometimes I cannot get the resource. I cannot be executed. Why? Only when all resources are available, I can process. Right? Sometimes may not be available. So it's starvation. Okay? And entire process may be stopped and hanged. So that's the also problem. No preemption is easy. You can back up, but that's not easy. So, for example, I process the 7 days a week and, for example, a year. So I have one more resource to access the memory, but which is occupied by him, his process. Then I need to release, hold the lock. Why? Because it's a preemptive. So once the resource is available, I need to start it again. Right? It can be doable, but not very practical sometimes. Circular wait. We need to check every time whether it's a waiting circular. In case of the circular wait, so we cannot request. We will see details about the circular wait. This is the most important characteristic of the deadlock situation. So, actually, deadlock avoidance. Logically, it is possible, but not always practically possible. Okay, sometimes it may not be possible, sometimes it's not reasonable. However, that is one of the ways to avoid the deadlock. Okay, so that is the deadlock. Actually, that avoidance, that is the prevention. I'm sorry. So that is the prevention. Every time I got confused, prevention and avoidance. So this is, I blame you, you said there's avoidance. Avoidance is a little bit different, we will see detail. So that is the first approach. You can prevent the deadlock. You can prevent, never enter deadlock situation. How? By allowing break one of the requirements. Okay, that is the one way. The other, actually, there are other solutions. So, to this, before we discuss about such a solution, as I said, the circular way is the most important characteristic of the deadlock situation. So, to define such a circular way, we have a number of processes, we have a number of instances, the resource n number of, and I number of the instead just so many. So to simplify such a resource and process, we are going to use the resource allocation graph, which is called the RAG. So what is a graph? Anyway, graph. Where is the two students? Where are they? So what is a graph?
It's a representation of data.
Representation, anything we are using the data, right? So we can use a vector, that is another representation of the data. So it's too general. So what is a characteristic of graph? What is a graph? It's a data structure, right? What kind of data structure? Where's your friend? What is a graph?
Same representation of.
Same as your friend?
But
They get used to my question, so I try to change the target. Yes.
every time you said the data structure, so how is a graph data structure?
Yeah. So what is a graph data structure? That's my question. I don't know either. So who can answer? What is the data? Anyone who already took the or taking the algorithm? I think in the algorithm class you learned about the graph a lot. No?
No, in algorithm.
No, in algorithm. What about
We
the
learn-
data
we-
structure course?
Advanced data structure.
Advanced data structure
Yeah.
course. So what is the graph?
I forgot.
You forgot. Yes. Yes.
It's untitled structure with the nodes and ends.
Yes. Graph always start with the definition like this. G graph is the set number of V, number of E, or sometimes different notation. It is fine. What is a V? Vertex. And what is a E? Edges. A number of the node. A number of edges. Edges can be defined as connection between two V1 and V2, or U and V. So you can define the E as the U, while the U and V belongs to V or something like that. The edges. Okay. So in other words, the graph data structure include number of node and number of edges. You have the similar data structure, which you are familiar with. What is that? You don't understand question, you don't understand the answer. So question is, this is a graph. You know what is a graph. Then there might be similar data structure as the graph, which is very, very popular. It's a tree structure. Tree has node and edge, but there might be relationship, parent and children node. What about graph? So this is a tree. Everybody knows the tree. We already see such a tree structure, process tree or something tree. If we are taking the database course, the B tree, B plus tree, or binary tree, or something like that, tree structure. What about the graph? Graph does not have such a relationship. It has only node and edges. One of the very popular example of the graph structure is what? Currently, some of the students are doing social media, like the Facebook, right now. What is a Facebook? Facebook, you have, and you are a friend. You make the friendship. Okay, it's the net. So graph structure. So graph structure is one of the very powerful to represent the characteristic of the data. Okay? So if you have the certain data, like the number of the process, number of the resource, and also you can request the resource, you can assign the resource, and you can release the resource from the process. And then we talk about something weight, circular weight, or hold and weight. How can we represent? How can we define such a model using graph. Okay, so graph is one of the nice data structure to represent relationship of the data. Okay. However, if you have such a parent and children relationship, it's a specialized graph. Okay, this is more general. Sometimes it has the direction like this. Friendship, when I make the friend with him, that doesn't mean he make the friend of me. I'm not sure the Facebook allow that, right? So there might be direction. It's a directed graph from here to there or there to here. Bidirectional or the unidirectional, it doesn't matter. But sometimes there's no. In resource-allocation graph, it's a directed graph. So which means from one node, we are going to use the node for the process. However, there are two types of node. One is